Good day, my name is Misha. I'm one of the developers of Embedano project, and today I want to show you example application that we developed for milestone 3 of our Catalyst proposal. Example can be found in MLabs Embedano repository under example app demo branch. Here you can also find detailed description and design documents of Embedano SDK, but as a quick refresher, Embedano SDK is an open source Rust library that allows you to perform key derivation and data signing required for Cardano on embedded devices. And this SDK not tied to any particular hardware, but as we stated for Catalyst proposal, our main target is Cortex M4 chips, and this is what we use as a hardware in our development process. And for today's demo, I will use NRF52840 development kit, and it will look exactly like this. And this is development kit board that built with Cortex M4 chip with floating point unit. So example itself is located in examples directory. In NRF52 demo folder. And the example consists of two parts. One part is demo client. This is an application written in Rust, and it will run on my laptop. This application will communicate with embedded device via USB port and with Cardano node via Cardano node socket. Basically what it will do, it will send request to embedded device, for example, to get public key or to sign some data, then get back response, build transaction and submit transaction to the blockchain. And second part is Embedano device. This is a firmware that I will flash to development kit to chip, and this will allow chip to respond properly on requests from the host application. And so key derivation and data signing will be executed on the chip. And this is the main script that will run demo on pre-production testnet. I will show it in more details when we get to actual demo execution. So main parts of this demo is of course hardware itself, then debugger. For the demo I will use GDB multi-arch debugger. This debugger will allow us to send or flash firmware to the device and observe logs that device will emit, so we can see exactly what is happening inside the device while we run the demo. Another important part is software that required to connect development kit to the laptop. And in particular, I will use G-Link GDB server. This will start special server that will connect to device and will allow to use this GDB multi-arch debugger to talk with the device through this server. And this is an optional part. If you want to run it purely on Linux or Windows, this is not required, but I'm using WSL, and when I will program firmware to the device, what will happen? It will create new USB device with USB port in Windows, and to forward this port to WSL, I will use this library, which is USB IPD. This is an open source library that you can just download and install, and it's pretty easy to use. I will show how to use it when we run the demo. And another important part to mention is Cortex-M Quick Start repository. This is what we use, the template that this repository provides. We use to build our demo. It has good detailed description, step-by-step instructions, how to set up everything. But we also provide Nix environment. So if you're using Nix, you can run that, and this is what I will use, and it has a lot of things already configured for you. And last note on examples, as you might probably notice, there are two more examples in example directory. First one, Chemo example. Chemo is an emulator that can emulate some hardware. And this example, you can see there how to run Embedano SDK functions and only those. So this is sort of like showcase of what Embedano SDK provides to you, but it will run it in constrained resources environment, like you run it on real device. And second example is STM32F. This is example for another board, STM32 Discovery board. And it's a simple version of today's demo. It also contains device and host parts. And device part is also firmware that built with Embedano SDK. And what this setup does is it runs in sequence a bunch of commands on the host, like get public key or sign data or another commands that will require device, and device process these requests using Embedano SDK and sends response. So there is no Cardano blockchain communication. This is just more simple example that you can also check out. Let's look on example application in more details. The idea is pretty simple. We want to get some sensor readings from device and send them to blockchain together with some check-in data. And the board I'm going to use in this demo has a temperature sensor. So we will query temperature sensor from the device, build transaction, and send it on chain. There is detailed description with exact steps of how example application works in milestone 3 example application markdown document, but code base itself is pretty closely aligned to these documents, so I will guide you through code base itself. This is main module of host application, the part that gonna talk with device, build and submit transaction. Here we're doing some initialization, reading arguments from command line like mnemonics, 4 keys, password, network ID to choose correct network, and we're going to use pre-production testnet and also device port that we want to connect to. Then we build script address. This will be address where we're gonna send our readings that we query from device, so it will work as sort of storage or registry for information we sending from the device. Then Node client is just a small wrapper around Cardano CLI. So to query Node and submit transaction, we actually use Cardano CLI and Cardano Node. And application has two main modes of operation, is submitting data to chain and verifying data to chain, and we go through each of them in order. So first is data submission. We start from device initialization, and this device struct is just wrapper around USB port, and you can find it here. It just hides some complexity of writing and reading to USB port to make demo code more clear. And here, after device initialized with mnemonics we passed as an argument, we querying sensor data from the device. And what is happening under the hood? This is the method we're querying sensor data. And here we're getting timestamp and preparing request with this timestamp to send to the device. And when device receives this request, it takes readings from temperature sensor, then concatenates both readings from sensor and timestamp, and sign this data with the private key that corresponds to derivation path that we passed to device request here. And then returns everything back to host application, temperature reading, timestamp, and the signature. Then we're requesting a public key that also corresponds to derivation path we chose. And this public key, we need to build correct transaction. We build address of this key so we can balance transaction and send change back to this address. And next, query inputs from node to balance transaction. And finally here we building and balancing transaction from the device address to the script address, and the only output to script we're producing will have a datum, and this datum will include the readings that we get from device together with the signature. After this transaction is built, we're calculating transaction ID because transaction not signed yet, and to sign it we need transaction ID. After we got transaction ID, we ask device to sign this transaction ID, again using correct password and derivation path. And after transaction is signed, we finish building transaction by adding witness. So we're getting signed transaction, and transaction is finally submitted to the chain. And after transaction is submitted, we will get a UTXO at script address that will have some minimum data that we have to put in the transaction, and the datum. And datum will hold the information from the device. And this brings us to second part, to the verification. For verification, we can assume that site that performs verification actually has a public key of the device, so we can use this public key to verify data. But here we just initialize device again, then get public key for the same derivation path that we used when we submitted transaction on chain. And then we just pull all UTXOs from script address, then parse the data that this UTXO holds, and then use public key data from the device and signature to verify that this data that we got from chain was indeed signed by the public key that we think belongs to device. So this is it for host part, and let's look at the device part. This is a firmware that will be flashed to device. First, we initialize some peripheral to get a USB port that will be used to communicate with device, and also we get temperature sensor to read temperature data from it. And after initialization done, the main loop starts, and it's a lot happening here, mostly reading, writing, and parsing data. And for example, I can show you where temperature requests are handled. It's happening here. So first we parsing request from host, which contain password, time, and derivation path for the key. Then we measure temperature by calling temperature sensor. Then we prepare everything for signing. We're checking that we have seed in device memory, which was generated from mnemonics. And also we parse derivation path that was sent to the device. And if everything parsed correctly, we chain together bytes from temperature reading and timestamp and signing this data using Embedano SDK. And after everything signed successfully, we just write response back to USB port, and this response is received by our host application. And to see where actually Embedano SDK called, it can be searched by this explicit import. So for example, here we're signing transaction ID using Embedano SDK function. And here we derive key pair using Embedano SDK function. This is, for example, what is called when host application is asking for public key from the device. And this is example of verification when we send in verification request to the device. And this is about it in terms of how code base is structured and part works together. And next we will see live action of how everything runs on real blockchain on pre-production testnet.